Okay, so since I need to have the microphone capable of picking up my voice, I'm going to have to sit here for the class. So I'm hoping that she can join us in a minute or two. But let's go back to looking at this part of the discussion. Um, and I'll ask this question to the four of you here in the room. Since I'm doing this, I'm actually recording the class. Do you want me to post a link to the recording if you want to review things? Would that be useful? Okay, I will be happy to do that. So we will we'll be looking at the consequences of medication um, errors in this one. There are lots of different errors. You'll see in this class some videos to watch. It's probably a good idea to do so, and read all of these extra links, such as this link to this document about cutting the risk of medication error. Part of it's going to be experience. What happens after you look at enough medication doses is you get an idea when something's wrong. And here is some of my advice to you. If you're working and something doesn't look right, don't assume that you are incorrect. You may very well be correct. And a lot of it has to do with instinct. If your instinct says something's wrong here, check it out. Always. Don't just dismiss it. I find, and I have found in my career, I've done that many a time, 90% of the time, I am wrong to dismiss my instincts. We develop these things as we work. And if it doesn't look right, it probably isn't. And it doesn't take any time. If you check it and it's fine, well, that's okay. There's nothing wrong with that either. But please get used to the idea that if something doesn't smell right, it probably stinks. Right? Check it. Always. So we have lots of different kinds of of mistakes that can be made. Most of the errors that actually get through the system are errors of the dosing of a drug. There are mistakes made, and we'll talk about how to avoid some of those. But there are mistakes made, and we have to learn from those mistakes. And so that's one of the things that you'll see here. We do have errors that happen. You walk in to look at a medication, and the medications are arranged in some order on the shelf. Sometimes it is alphabetically. Sometimes you'll go into, especially a specialty clinic, such as an infectious disease clinic, and they'll have the anti-infectives, the antivirals, the antibacterials, the antifungals, and so forth. They'll have those in a special place. Any other drugs they might have to use would be elsewhere. So people will often, when they make an error, a lot of the errors are basically grabbing the wrong bottle. There was a case 10, 15 years ago in Florida where a 10-year-old boy died suddenly. And of course, when that happens, the very first suspicion that the police have, at least, is abuse. Okay? So there was no sign of abuse. So the medical examiner who was doing the autopsy on this child decided that she would send a tissue sample for drug testing. And it turned out that there were lethal doses of methadone in this child's system. Well, that immediately raised suspicions again about the family, right? No indication that this family had any drugs of that sort in the house. It turned out that the child had ADHD and was taking Ritalin. Ritalin is an expensive drug. The generic form of Ritalin is methylphenidate. And the pharmacist decided to try and save the family money by giving him methylphenidate. It would have cut the prescription cost in half. But he grabbed a bottle of methadone off the shelf of his pharmacy by mistake. And the dose of Ritalin was such that the methadone dose that he was given was fatal. So the pharmacist, as you can imagine, was in real hot water. I think he lost his license.
Well, you should for something like that if you're gonna, like, I get like medications are expensive, but like if you're trying to like shortcut it to try to like help out a family, you should have like double check your stuff, because now that's a child that they cannot have back.
That's
all
right.
for a simple mistake, when he should have literally just double checked the bottles and made sure that the dose was the same amount that it should have been with the original prescription to
Yep.
start with. Like that's
You should have.
really bad. I'd be really angry. People like that really should keep their license. You know what I mean? Can't really recover.
No, you can't. You cannot recover from it. And you know, as a parent, I can't imagine what it'd be like to lose a child.
Me either.
So it really is something to think about. So these kinds of mistakes occur. That is an action-based mistake. It's a human error. It's grabbing the wrong bottle and then forgetting the 3-check rule. Whenever you're messing with a prescription, you should check 3 times. First, read the prescription and make sure you understand it. In this class, I'll show you some examples of prescriptions. And what you'll be doing is interpreting those as one of our in-class activities, handwritten by doctors. And I guarantee you that everything you've heard about how horrible doctors' handwriting is minimizes how horrible the handwriting is. It's really nasty. It can be very hard to interpret these. So you should check at the time. You should check when you get the prescription bottle off the shelf. You should make sure that it is the right prescription bottle. And then before you actually start filling, because usually you stack these things up when you're working, when you start filling it, you do it again. You check a 3rd time, always. And then if you're working there in a pharmacist, which is not what you're being trained for in this program, but if you're working in a pharmacy as a technician, the pharmacist by law must check it as well. So you really have a 4-check process. And this is one of the ways we can minimize errors. But these things happen. Errors can occur that can be that can be related to these human actions that we take, action-based errors. They can be based on knowledge. You may not know enough about the drug. And I can remember when I was a kid, doctors would routinely check a publication every doctor's office had, the physician's desk reference, which was a compendium of all the drugs available at the time the thing was published, and check to make sure that he was doing the right dosing. Now, of course, we can do that online. In fact, I don't know if you okay, she's not on yet. I don't know if you have done this or not, but there is a product, a software package that you can load onto your smartphone. It's called Hippocrates. It's free. You can also buy it and get more capabilities, but it has a lot of reference material. You put it on your smartphone, call it up, and you can get a lot of drug information. When you go through some of your other classes, hematology, urology, or urinalysis, and so forth, you can call up the expected blood test and urine test values as well. These are all available on this, and it's free. As I said, you can pay for it, which I suggest you may want to consider when you're working and have the money to pay for it. But you can pay for it and get a lot more capabilities. But it is quite a useful tool to have, and it's updated regularly. So you can put that on your smartphone. That again helps understand what's going on. So the prompt on this discussion is to discuss the pitfalls of drug calculations, of improper drug calculations, and describe what can happen if it's not done properly. So think about this. There is my post on this particular discussion at the beginning of the week. As you all remember, we post at the beginning of the week, goes into some ideas about that topic. I don't want to prompt you to have a preconceived notion here. The second discussion is about units of measure. Units of measure are critical. The pharmaceutical and drug world, medical world, functions in the metric system of measurement. All of you should have been exposed to that in high school, but you may or may not have used it since. We have the United States is officially, the official measurement system of the United States government is metric, but the unofficial system that's used by virtually everyone in the country is what we call the household, or English, or whatever you want to call it, a number of different names, system of measurement. And we still use that to some extent in medicine. For those of you with kids, you remember when you've been given a prescription for a drug like amoxicillin or something, you're told to give so many teaspoons per dose. We are starting to move more toward giving metric doses, but for the most part, we dose using the household system. We do all the calculations, however, in metric, and then do the conversion to the household at the end of our calculations. So we have to be able to be what I call bilingual in terms of measurement systems here. There are a lot of ways of looking that. I'm going to give you guys a handout probably later on this morning about converting between measurement systems. I'm going to give you a lot of handouts in this class. Because I find that it's useful for you to have those when you're at home and working on assignments and stuff, to have those things there. But we have a lot of systems here. As it said here, we have our measurement system is involved in weight, or mass, as is a more accurate scientific term for it, and volume, as well as to some extent length. We all know that we We measure height and weight. You'll be doing that a lot. Mostly we use the English system, inches and feet, when we're doing height and weight measurements. But in reality, it doesn't matter. We can convert between the two very easily. And if you remember, I don't know if you had a chance to use the scales and stuff that we have in the lab, but they use both the metric and the English system on their weight and on their height measurements. So it really depends on your clinic and the population that you're serving. And as we evolve more toward standard usage of metric, we will see those change. The metric system has a lot of wonderful consistencies, and I'll get those will be covered partially in my discussion. We have again some videos here that are worth looking at, and we may be going through those later on today here in class. Okay. Welcome, Kayla. Glad you could make it. So we will be. I'm recording this, so you can go back and pick up the material that I've recorded before you were able to get on.
Sorry, I just started hearing you.
Say that again, please.
I just started hearing what you were saying.
Right. I'm recording this so that you can go back and get the material before you got on.
Oh, okay.
All right. So we're talking about the second discussion. Each week there's going to be two discussions. This week we're looking at discussing in the first discussion the consequences of calculation errors in drug administration. And in the second discussion, we're talking about measurement systems. We'll go through more of that in a little bit. I have the prompt here is related to accurate measurements. My initial response here is actually quite lengthy, but it goes into a lot of material that is really important for understanding how to use different measurement systems. We have lots of ways. I'll talk a bit later to this morning. I'll talk a little bit later this morning about some of these measurement systems and about the advantages of them, and also some alternative ways that we measure what we call the potency of drugs. In other words, the amount of drug that's in a dose. And there are many different ways of doing that. So we'll get into a discussion of that later on. The assignment for this week is really about measurement systems and conversions. One of the things that is here is when you get down to the prompt in the assignments, there is a document to download. Now, I have been through this document. There are some errors in it. I will print it out on the break and give you guys a copy. Kayla, I will email it to you.
Okay.
So that you can have it right away. I'm hoping you can make class the rest of the time, because we will be doing some in-class exercises that are important. And I understand you have a wonky work schedule, but let's work around it, okay?
Yeah, I'm trying to get a new job.
Ah, wonderful. Good luck.
Thanks.
So, so you'll be downloading these. There are errors. We will go through them in class. There are some errors. Some of the errors are sort of more almost grammatical rather than confusing. But there are a couple of them that are actually can confuse us if we don't discuss them. We're trying to get those fixed, but that hasn't been able to be done yet. So, and on top of that, even though it's a Word document, they're locked and I can't modify them. So, or they'd be fixed already. So anyway, we have these that you'll download each week. They are 6 or 7 pages in length. So therefore, what I will be doing each week is printing them out for you, because the way they come out, they're in color, and the color differentiation is very useful. So I'm going to print them out for you each week. And this week's I will print out later today. That was the only one I could actually modify, so I'll be giving you a corrected copy. So we will be working with those, and they will. I'll give you a hint on this. What I want you to be doing with with this is using it as a means of carrying through. You'll notice when I've got this up here on screen that the word preview appears here. There's a reason, and that's because each assignment is actually a quiz. And what those quizzes are is actually using the worksheet. The quizzes are based on the worksheet. So you use the worksheet to do your calculations, then take the quiz using the answers that you calculate. Now here's where I will ask you, if you run into something and you calculate and you check and you calculate and you check, and then your quiz on that same question tells you you're giving the wrong answer, let me know. I have tried my best to check through and make sure that the quizzes are correct, but occasionally some things will slip through. So let me know if there's a problem. I can fix it. It's easy for me. You can't, but I can. So we'll make sure that this is all correct. I think I got it all done the last time I taught this class, but there's a possibility I missed a couple. So the assignment is actually turns out to be a quiz as well as an assignment. The assignment, of course, is to work through the worksheet, which I want you to do. So let's back up. And then, of course, there's an assessment each week. As I said before, you're going to wake up? There you go. As I said before, this is set up to where all assessments are set up for 3 attempts. If you see an assessment that somehow is not for some reason, let me know. Again, it's easy for me to fix. And, as I say, errors happen all the time. Sometimes I just flat out miss things. But there's no time limit. You get multiple attempts, we take the highest grade. And again, remember, some of these may require a written answer. And so you will not be given a grade for it necessarily until I check it. So if you see that there is something that's not being graded, it's because I have to physically go in and check the answer. It's not a big deal. So I will take care of that regularly. So you'll be able to see the correct answers after your last attempt. Okay, so if you don't get 100%, you'll at least be able to see where you made your errors. Okay, and learn from that. Learn from those. Use these as a learning opportunity. Okay, so that will be the structure. We go back here. You'll note that we have an in-class activity each week. And that one I forgot to change. The last time I taught this, we didn't have, I had one student. So the assignment worksheet was the in-class activity. This mod, I have a series of dosing problems and prescriptions that we'll work through. So in reality, the in-class activity will be related to the material we're covering this week, but it will be different from your assignment sheet. Okay? And as I said before, I want you to work together. So here we'll get this work done in a different way, and I will adjust these assignments to reflect that. Okay. So any immediate questions? Okay. Okay, good. So let's talk about a couple of things here, especially to do with how we describe dosing in our calculations. But there's one or two things I want to emphasize first, and that is that when we are doing numbers in medicine, we have some very strict rules to help us avoid mistakes. One of those rules is that many of our doses will be calculated as decimals, as decimal doses. You might have a dose of 1/4 of a gram, 0.25 gram. Well, when we write 0.25, for the most part, there's a decimal point followed by 2.5. When there is no number, no digit in front of the decimal point, to the left of the decimal point, we place a 0. Why? That 0 tells us that whether or not we see it, there's a decimal point next. If we just say 0.25 and the decimal point doesn't come through, and quite often we see these things done electronically, by fax, by email. If the decimal point doesn't come through, we have just overdosed the patient by 100-fold. Clearly, that's not a good idea. All drugs are toxic. I don't care what the pharmaceutical industry says, and I spent 25 years in that industry. I don't care what they say, all drugs are toxic. So it doesn't matter. That's why we have to be accurate. Now, the other thing we don't ever do is in science, a lot of times, if we want to specify that a number is exactly 25, we'll say 25.0. We'll put a 0 after the number. We call that a trailing 0. We never do that in medicine, ever. And the reason, again, is because if that decimal point doesn't come through, we've just overdosed the patient by a factor of 10. So one thing I will say, I have never seen a physician make a mistake with the decimal point, either leave off the leading 0 or put a trailing 0. I've never seen one do that. That is emphasized so heavily in medical and nursing schools that you just don't see that error. So it is really ingrained that this is critical. So when you are writing numbers, keep these rules in mind. Always a leading zero if there's no digit, digit 1 through 9 to the left of the decimal point, and never a trailing zero. Okay. So that is something that is critical. Now, all drugs are labeled. Drug labels, when you see a drug label, it will tell you what is the form of the drug. Is it a tablet? Is it a capsule? Is it a liquid? It will tell you that form. It will also tell you how much drug is in each of those units, each tablet, each capsule, each number of milliliters of a liquid. It will tell you that. And they're always in the metric system. Now, in the metric system, we have for weight or mass, to be more scientifically accurate, we use the gram. And that is always abbreviated G, never GR. Always G. I'll come to what a GR means in medicine later. But gram, and then we have a different, we have different levels. In the metric system, every step, every multiple of 10 has a very specific prefix that tells us what fraction of 100 or 1 each of those units is. In the medicine world, we dose in grams, we dose in milligrams, which is abbreviated mg, and a milligram is a 1 gram equals 1,000 milligrams. So milli means 1/1000th. So a milligram is 1/1000th of a gram. Now, to put this in perspective, a gram is about 1/30th of a standard ounce that we use to measure. So grams are pretty small. Okay, it's actually 28.97 or something like that grams to the ounce. But 30 is a good enough approximation. We also have micrograms. And that's abbreviated MCG. Now, you may see in some texts, especially older ones, an abbreviation that looks like a U with a tail on the wrong side, or a Y with the tail on the wrong side. That is the Greek letter mu, and that is the scientific abbreviation for micro, which is 1/1,000,000th. So there's 1,000 micrograms to a milligram and 1,000,000 micrograms to a gram. Okay. This, however, can be very confusing because it looks an awful lot like a U, which has a different meaning. We never use it. In medicine, we always use MC. So we have, so a milligram is 1,000 micrograms. Okay? That's as far as we go. We don't use anything smaller. Microgram, most drugs are dosed in milligrams. There are a few that are dosed in grams. And there are a few that are dosed in micrograms. Drugs that are dosed in micrograms are a good example of that is a drug known as digoxin. It's used for heart failure. And those drugs are extremely potent, very potent. And therefore, we have to be very careful with them. It's very easy to overdose patients when we're dealing with drugs that are dosed in the microgram range. So we will see these. So we'll get in. I will also be providing you with some conversion rubrics that you can use to memorize all of these conversions that we use in medicine. It's not designed to give you a complete metric system education in the various levels, but it will tell you what we work with in the medical field. And so these are the standards. Most drugs are dosed in gram, milligram, microgram amounts. Okay. Drugs are formulated into a dosage form that you're familiar with, tablets, capsules, etc., along with usually fairly relatively, compared to the amount of drug, large amounts of materials we call excipients, which is other components that have no biological activity, no pharmacological activity. Excipients are things like starch, sugars, and you'll see, if you look at a description of a drug formula, you'll see a dozen different things in there that are used for purposes of making a unified formulation that's consistent. Usually what you will see is things like a 200 milligram ibuprofen tablet that you're probably all familiar with. The amount of ibuprofen, if you compress that into a crystal, would be smaller than a crystal of sea salt. Okay, very small. But we can't compress most drugs into a crystal very easily. First off, the crystals won't dissolve in our stomachs. That's a major problem, right? Second off, they don't like to be just compressed. So we use these excipients as a matrix to deliver a dose. It also makes it possible for the quality assurance on those things to be very, very tight. In other words, that 200 milligram ibuprofen tablet, if you took 1,000 of those and measured the exact amount of ibuprofen in each one, there would probably not be a 0.5 milligram difference spread out. It would probably range anywhere from 199.5 milligrams to 200.5 milligrams. In other words, less than 0.25% error. These things are formulated for that. Now, we put in things like, if you read through there, you'll see things like silica. Well, silica, to be honest, is sand. But we use it to allow things to flow through the tableting machines, so that what goes through the machine stays very uniform. So these things are very carefully formulated. These excipients have no, as I said, have no pharmacological activity. They come off a list that we call the generally recognized as safe list. They're materials that have been shown to have no biological activity. We usually do some experiments to be sure that there's no interaction between the excipients and the drug that's going to make the drug unavailable. So we do a lot of experimentation when we're formulating these things. They're very carefully done. But you can look at that. If it says 500 milligrams on the tablet, you can bet there are 500 milligrams. As we go through calculations, we'll see that there are some calculations that have to be approximated. We have a lot of leeway in our calculations sometimes. So we'll come to that later. But the FDA and medicine in general is very, very comfortable with with the ability that we have to manufacture these drugs very, very consistently. And the pharmaceutical companies will actually recall batches if they're not consistent. In fact, that's one of the major reasons that we have recalls. Something isn't quite right. And we don't know what kind of safety implications they have. So pharmaceutical companies will voluntarily recall a lot of products for that reason, if they're not perfect, if they ever get out of the manufacturing facility in the first place. So we have very consistent results. We have consistent formulations here. So what other ways? The amount of drug, by the way, I'm going to use the word potency. The amount of drug in a tablet is its potency. So the 200 milligram ibuprofen tablet has a potency of 200 milligrams. A 500 milligram tablet of amoxicillin has a potency of 500 milligrams of amoxicillin. And potency is always related to the drug itself, because different drugs have different potencies, have different biological effects. So another thing is that most of our drugs are delivered like this, but you probably are familiar, hopefully not personally familiar, but you're probably familiar with diabetics who take things like insulin, right? And they dose it in what we call units. Okay, a unit of insulin is an amount of drug that has a biological activity. We dose it that way because although today we have ways of manufacturing insulin that we could actually give microgram amounts, traditionally insulin was actually isolated. The original isolates were from pig pancreas. This is work done in Denmark, where this work in the early part of the 20th century, a bunch of Danish physicians and experimenters were looking at how they could treat diabetes. They knew that their patients needed insulin. Insulin is something that we call a highly conserved protein, which means that the insulin that we can find in pigs, goats, cattle, sheep looks essentially exactly the same as the insulin we find in human beings. In other words, it's very consistent across species. So insulin is insulin, no matter where you get it. In fact, virtually every animal life form on the planet Earth has insulin, except for a couple of species of spider, kind of weirdly. Yeah. Yeah, we figure they must be very primitive forms, primitive organisms before they evolved further. But essentially, we all have insulin. And so we can isolate pig insulin. That's where it came from. And why in Denmark? Well, Denmark produces more pigs per capita than any other place on the planet. In fact, when you go to a barbecue place and have baby back ribs, 90% chance they came out of Denmark. That's where we get them. Why do I know this? I have a daughter living in Denmark. So we've learned these things. But we have a lot of information about that. We measure that in something we call units. And the reason we did is because when you isolate these things from an animal source, then each batch is different. It's going to have a different amount of this protein, insulin, this protein hormone that's insulin, going to have a different amount in each batch. So we had to have a way of standardizing it. And so a series of assays have been developed that we call biological assays. They test this thing against standards that are established in the industry. And then we have, and we establish what we call the number of units that is in every batch of volume and in some volume. And then we dilute that such that the standard insulin that you take today, if you're a diabetic or if you're in a hospital and giving insulin to patients who are on a glucose or a dextrose drip line and their sugars are skyrocketing, is 100 units per milliliter. So that we take, if you look at an insulin syringe, and we have some in the lab, we'll actually take a look at some of those. I think we have some in the lab. Instead of being graduated in milliliters, they're graduated in units. But it could be just as easily milliliters, because every 1/100th of a milliliter contains 1 unit. So we use units for these biological products. Insulin is one, growth hormones, various antibiotics, which are isolated from various strains of molds and yeasts and other bacteria. We use these things because the way we have to extract them and get them is non-standard. And so we've standardized this measurement system so that when you see a bottle of insulin on the shelf and it says 100 units per milliliter, there are 100 units per milliliter, no matter where it came from. Okay. Another thing is that occasionally we have to do dosing of electrolytes, potassium chloride, sodium bicarbonate, and so forth, into our patients. Those come out of, those use a different measurement system called the milli-equivalent. Now, equivalent has to do with chemical combining power, which is, but so we have, when we see a dose of, say, potassium, you'll see this with potassium tablets. And you'll see something that'll say 10 milliequivalents per tablet. Well, we can translate that into milligrams, but it really boils down to the old biological assays we used for determining how much potassium the patient had circulating in their blood. From your A&P classes, you either have learned or will learn that we have a balance of potassium and sodium chloride in our body, and if that balance gets out of whack, it can cause very serious heart implications. So, so we monitor that, and if people require potassium, they will be given potassium tablets or sometimes injections of a certain amount. And why these things occur when patients are on water pills, diuretic drugs, which reduce the water buildup that's associated with things like congestive heart failure. We start not being able to process fluids out of our bodies very efficiently. Some of those diuretics actually cause us to lose potassium, and that's not a good thing. So we will give potassium substitutes, or supplements, to our patients to try and maintain that. So these are all dosed using the milli-equivalent. Now, we will learn when we are doing our dosing calculations that it doesn't matter if we're talking about grams, milligrams, micrograms, units, or milliequivalents, because we don't dose in that fashion. We don't tell the patient, take 50 milligrams of, Lasix. We tell our patients to take 1 tablet. So the potency unit is irrelevant because our patients don't take drugs in that fashion, nor do we dose them. If it's an injectable dose, we dose by a number of milliliters. And we have to calculate that. So when we're doing our calculations, we'll be calculating in terms of solid dosage forms, we'll be calculating a number of tablets or capsules. We'll be calculating either, and for liquids, it'll be a number of milliliters, which if it's oral, we may convert to teaspoons. And other than that, that's all we ever calculate. What we're going to give our patient is a physical manifestation of the drug. Okay, so it's time for a break. It's 11:02. So let's go ahead and take a 10-minute break. And I will go ahead and print off some stuff during that break and get it back to you. Okay, Kayla, do you have any questions?
No, everything's good.
Okay. Okay. So I'm going to shut the recording off at the moment so that there's not a 10-minute.
Thank you for doing that.
You're welcome. Give Paul and Beatrice a couple of more minutes to get back. Okay. Okay, let's go ahead and get started. In the two handouts that I have just given you, the first one, the calculation introduction, is the handout that comes with the week 1 assignment. I made some corrections on it. And they're there in blue. You will see that there are some videos shown on this document. In order to access those videos, obviously you'll have to go ahead and download it, which is no big deal. But you should watch those videos and we may bring a couple of them up anyway as part of the class right now. The second one is about conversion factors, and I'm going to concentrate first on the metric because all of these conversion factors work the same way. The object here is how do we convert from the various factors from one to the other, grams to milligrams, but also how do we go back from milligrams to grams? And what we have is on this, at the top, you'll see the first one, kg is a kilogram. A kilogram is 1,000 grams. So there's a kg, an arrow with 1,000 over it. The 1,000 is the conversion factor. If we go to grams, we multiply by 1,000. So 2 kilograms is 2,000 grams. So if we are going in the direction of the arrow from left to right, we multiply by the number of arrows we have to follow. So if we want to know how many milligrams are in a kilogram, we're first going to multiply by 1,000 to get to grams and then by another 1,000 to get to milligrams. In other words, there's 1,000,000 milligrams in a kilogram. If we are going in the other direction, we divide. So if we want to know how many grams are in 500 milligrams, we divide by 1,000. 500 over 1,000 is 0.5. So that would be 0.5 grams. Okay. In the volume, is the basic unit is the liter. We always use a capital L. A small l can be confused with a 1. So in medicine, when we're talking about anything to do with volume, we use a capital L. So we have liters to what we call deciliters. Why do I put that in there? Because all of your chemistry results that you'll see in hematology and in and your other classes where we are looking at measuring the blood levels of various components are given in a number of, say, milligrams per deciliter of blood. So what that means is 1/10 of a liter, 100 milliliters. Okay. Notice that I use a capital L all the way across. M capital L is the abbreviation for milliliter. I have on the other handout, the calculation introduction handout, They list as an abbreviation for milliliter, M capital L and M small l. I crossed out the M small l because we never use it in medicine. Don't get into that bad habit because it will confuse people eventually. And for lengths, the meter is a standard. A meter is approximately a yard. It's actually 1.1 yard. There are 100 centimeters. That's a measurement you've probably seen already. 100 centimeters to a meter. And there are 10 millimeters to a centimeter. There are also 1,000 millimeters to a meter. Now, we rarely use millimeters in medicine. However, we see it a lot. We also can convert back and forth. I'll get to some of these other measurement systems in a minute. But this rubric works, and the way the rubric always works is if you are converting from larger to smaller, in other words, left to right on this rubric scale, you multiply. If you're going from smaller to larger, from right to left on this scale, you divide. Okay? If you remember just those two rules and the order of these things, you will not make mistakes. Okay? So if we look at this calculation introduction document, there's a bunch of abbreviations, some of which, as I said, I've corrected. The other thing is they use the standard cookbook kinds of definitions or abbreviations for tablespoon and teaspoon. We don't use capital T or small t. It's too easy to confuse them. And since there are 3 teaspoons to a tablespoon, if you make that mistake, it's supposed to be a teaspoon, and you use a tablespoon, then you overdose by a factor of 3. So again, we want to be careful about that. So we always, in fact, there are many organizations and a lot of hospitals right now that do not allow any abbreviations in medical records at all.
Oh, really?
Yes, because too many of them can be mistaken, and it's a lot easier to say none than to say, oh, you can't use these, because that list will always be forgotten. Plus, it'll change as we find mistakes being made. But a lot of hospitals have gone to no abbreviations at all in medical records. So again, this is all about patient safety. If it affects patient safety, that's where we go. If we can improve patient safety, we use that. And there have been a lot of mistakes in over the years because of misinterpretation of abbreviations. So we're learning. Unfortunately, it's been kind of hard on patients, but we have learned. So and it states right here, they can be a major source of error if improperly used. So we need to make sure that we use them. I have another document that I'm going to dredge out and probably give you guys copies of that lists all of the abbreviations that there are. There are probably a couple of thousand abbreviations. And unfortunately, some of them are confusing because they can be the same thing. One of the reasons that hospitals wanted to get rid of abbreviations is the abbreviation MS. MS can mean multiple sclerosis. It can mean morphine sulfate. It can mean magnesium sulfate. All of these are very, very different, and we cannot afford to make those mistakes. So that is one of the things that we look at. So we want to be careful about that we understand these abbreviations. Now, let's take a look. We talked about the metric system and mostly about weights. Now I've mentioned volume. The basic volume is a liter. That's approximately a quart. Okay, it's a little bit more than a quart. And so these are good rough estimates as well. And a milliliter, which is what you'll mostly see when we're dosing, happens to be about it happens to be about 1/30th of an ounce. There are approximately 5 milliliters to a teaspoon. So that's another good conversion. It's not exact, it's really 4.8, but it's a close enough approximation that it's safe to use at 5. It's also a lot easier to calculate for most people. But we use those as well. We have the rubric here for the household uses quarts, cups, ounces, tablespoons, teaspoons, and then to milliliters. And again, if you're converting milliliters to teaspoons, you are moving from right to left on the rubric, and you divide by 5. So if the dose is 30 milliliters, you're going to give 6 teaspoons, which you can further convert to 2 tablespoons. Now, a lot of times you're going to see dosing with these little cups that have both milliliters and teaspoons on them. Okay. Then, we really want to be careful that the patient understands which scale to use. Okay. We also have other things. We have oral syringes, which are invariably in milliliters. So you need to be careful to explain. One of the ways that I've seen it best done is to take that oral syringe and take a Sharpie and mark on it what the dose is supposed to be.
That's what I do with my medicine because it has a small syringe, so that's what like mark where the dosage is because it's easy to forget and it's easy to like overdose like medicine.
Good advice. Yes, good advice. The first time I ran into that was actually from a vet.
Oh, really?
We had some work done on one of our cats, and we had to give the cat some antibiotic, and she's sitting there. The young woman in the office is sitting there and talking about, well, you give the cat 2 milliliters. Let me mark on there what 2 milliliters are. And I bit my tongue real fast because I was going to say, I'm a chemist. I've been dealing in milliliters longer than you've been alive. And I said, no, let her do her work. Let her do her work. And said, thank you, and walked out. But really, even if you already know, let them do their work. Then they know they've helped you. So, and the cat was impossible. We lost half the medication. But if you've ever tried to dose a cat, you understand exactly what goes on there. So anyway, but we will. The other thing is there's hollow-handled spoons. Have you ever seen those? As well, and they're graduated the same way. And again, just mark it on there. Very, very easy to do. Okay. There is an old, so there's where the household system comes in, is in dosing oral liquids. That's where we get that. Okay. Now, there's something called the apothecary system of measurement. This is ancient. It really came into its own in actually the European Middle Ages, but it actually goes back to ancient Greece as a way of standardizing doses of medication before we had a standard medication system. And the apothecary is just another word for pharmacist. Okay? So the apothecary measurement of weight is the grain. Where's that here? And that's abbreviated GR, which is one of the reasons that we really emphasize when we're talking about the metric system and we're talking about grams, we make sure that people understand that it's G, not GR, because a grain actually is either 60 or 65 milligrams, depending on the drug. If you look at one of the older bottles of aspirin, you'll see 325 milligrams. And then below that, it might say 5 grains. Well, if you divide 5 into 325, you get 65. So it's 65 milligrams per grain. On the other hand, a very potent drug, nitroglycerin, which we use to treat angina, which is heart pain that's related to incipient, potentially a heart attack, it's 60 milligrams per grain. So that's why we don't use apothecary weights anymore as a general rule, because it's not consistent. And on top of that, what's a grain? Originally, it was a grain of wheat. Well, that's great. Are we talking about Bulgur wheat or Nebraska wheat? Very different size grains. Okay. So that's one of the reasons that we standardized and said, okay, a grain is 65 milligrams or maybe 60, depending on the drug. We basically don't use it. And in fact, again, a number of hospitals have outlawed, or I should say banned, the use of apothecary measurements. Volumes, we will see in terms of, and on the other hand, as well, if we're looking at a metric drug, we're going to see, say, 500 milligrams as the dose. If we are looking at grains, we're going to see GR5. In other words, the number goes after the measurement unit in the apothecary system. That also helps distinguish it from the metric system. But again, we don't want to use that, except that you will see it. There are still some old physicians who will use that simply to make trouble, I think. Another thing is the volume. We have a fluid ounce, which is pretty much a standard fluid ounce that we would get out of the English system, 2 tablespoons. But that's divided into 8 drams. And you will see the word dram used consistently now in the pharmacy to describe the size of pill bottles. And they're listed in the volume in drams. And the little 1 dram liquid that a lot of people that do things like aromatherapy, that sell the essential oils and stuff for that, they're in those little bitty bottles about yay tall. That's a 1 dram vial. Okay. So we still use those for some things. But you probably will not see any extensive use of apothecary measurement. We throw it in because it is taught as part of this class, because it still exists. It still comes into play occasionally. There are also, there is a measurement called a minim in terms of volume in the apothecary system. And again, we hear this. A minim is a drop. Now, you all know that drops are different sizes depending on the size of the opening they come out of. So we have some fairly standard droppers that are used in medicine that very consistently will deliver a drop size that is such that 20 drops will make a milliliter. Okay? But not all of them are that way. And of course, you know, anything bigger than that is going to have something else. This is another reason we don't use the minim. There's another reason. The standard conversion is 20 minim per milliliter, unless you look at some older texts when it's 16 drops per milliliter, or even 15. So even more confusion when it comes to volume. So we don't use the apothecary system because it simply isn't accurate enough in today's world. We have the ability to measure these things much more accurately, but you'll still see it. However, one abbreviation for drop that you will see is GTT. Where does that come from? It comes from a Latin word, gutta, which stands for drop. Okay. So you'll see that, and especially you'll see that in ophthalmic medications, things like glaucoma meds and liquid antibiotics that might be going into an eye for an eye infection, anti-inflammatories to try and reduce the conjunctivitis that people have when they have eye irritations. They'll say 2 GTT per eye or something like that. So you'll see that used a lot, the abbreviation for drop. Okay. So the handout that I gave you will help you with some of these, and there are some examples there which I'll let you explore on your own in that. So having said that, let's take a look at some calculations, and again, as a start. Some are fairly easy. And some are not so. But what we're going to do, this thing goes into some interpretation using the abbreviations. We'll do some of that on Thursday in class, in some of our in-class work. We'll be looking at interpreting these prescriptions. So one of the things you need to be doing is reviewing this and learning this terminology and these abbreviations. You've probably been exposed, if you've already taken med term, you've probably been exposed to part of this. So this is going to
all of the term, like abbreviation, like work or whatever, like this whole like I think I got this from Karen or Nate from med term or something like that.
Super.
So wait, does that mean I can use them in this class?
Sure.
Some of this stuff?
Yeah. Anything you've acquired in other classes that'll help you here, bring it. Use it. Because you're not supposed to ever forget that. You'll always have it at hand. So I'm all for doing things the smart way. Okay. So we'll look at that now. This week's assignment, is doing a lot of these conversions, and learning about some of the math. So I want to move to some of the math. This starts on page about 6 of the handout that I gave you on the calculations handout. And the basis for all medical dosing calculations is called proportion, ratio and proportion. Now, ratio and proportion is just another way of saying fractions. And I know some people, they hear the word fractions and they freak out. I hope not in this group. Fractions are pretty simple. Fractions are simply a relationship between numbers. They express the number of parts of a whole. So you can think of it as if you start off and you have a pie, and you're particularly fond of this pie and piggy, so you only divide it into 6 pieces, right? Each piece is 1 of 6, or 1/6. Okay? That's all a fraction is. It's a number of parts of a whole. The number on the bottom, called the denominator, is the whole. The number on the top, called the numerator, is the number of parts of that whole. Okay? And you can have fractions where the numerator is bigger than the denominator. That just means you have 1 plus, a whole plus. That's all. Okay? Fractions are fairly easy to make use of, but we can look at that as, so here, this is 1/6 of the pie. So to express that as a ratio, we're saying that that is 1/6, meaning that this thing is only a portion of this. It's a small part of the whole. Now, this is called a ratio. What's the difference between it and a fraction? Nothing. Okay, we'll just leave it at that. Just another way of looking at it, right? But one thing about ratios, we also have this word proportion. A proportion is a pair of equivalent ratios. So let's say that we have, let me get a different color for this. Let's say that we're really piggy and take 2 pieces of this pie, right? So we've had 2/6. Right? Now, you all know that we can divide the numerator and the denominator by the same thing, and the fraction remains equivalent, right? So if we divide 2 into each of this, we get 1/3. Now, so 2/6 equals 1/3. That's a proportional equation. Okay? And the whole basis of dosing calculations is that we have 3 of those 4 numbers. And we can then calculate the 4th using algebra. Now, you've all had algebra, either in high school or in your GED training, whichever way you finished out your secondary education. And I will say this, I think GED programs turn out to be better educational experiences than most high schools. That's my opinion. So I have no trouble with GED programs. A lot of people sort of sneer at that. Not me. My experience here has been our GED graduates who come in here and gone to school are often some of our best students because they're better prepared. And especially when they go through Laura. She was really getting well prepared. So You know, so it doesn't matter. But the proportional equation, 2/6 equals 1/3, means that if we want to know, we can ask ourselves the question, how many sixths equals 1/3? That's a question mark in case my horrible writing is not quite clear. So maybe we already know the answer, but we can solve this mathematically by simply replacing the question mark with an X and solve for X. And y'all remember your, I like that Katie gave us a lot of colors. The first thing we do is cross multiply. So now we take this and we make 3x equals 6. And now we divide by 3 and we get 2. Okay? That is as complicated. Setting up sometimes can be a little more complicated, but that's almost as complicated as dosing calculations get right there, because we have all the information. So I'm going to give you a simple example of a calculation for a drug, okay, a prescription. And we'll start off by writing out the prescription. This is going to be rather typical. Okay, so Michaela, since you can't see that, I will, or maybe not clearly, amoxicillin 500 milligram PO/TID times 10 days. Now that reads in English, amoxicillin, give 500 milligrams by mouth 3 times a day for 10 days. Okay. Using that, that's what the doctor would write. When you get that prescription handed to you, you're going to be told to take so many tablets 3 times a day for 10 days. Okay? Simple. So the question is, what information do we have to try and set up our dosing calculation? And I'm going to step aside slightly and give you a formula that will be the basis for everything we do. And that is going to be X, which is the amount of drug taken per dose, which is really the units of drug in terms of tablets, capsules, milliliters, whatever. Per dose is going to be D times V over H. What are D, V, and H? Good question. Glad you asked. D is equal to the dose prescribed. In this case, it's 500 milligrams. We got it right off the prescription. No calculation involved, just read the prescription. V is what I call the vehicle. Now, in the paperwork you'll see, you may see this as Q, which means quantity. However, that is not an accurate enough description for me. The vehicle is the physical form of the drug. Okay? Okay, the physical form. That will be a tablet or a capsule, or maybe a suppository. Or any other solid or semi-solid form. And we have lots of names, but they all boil down to tablet or capsule or suppository. And that is for solids. For liquids, it's always a milliliter. Always. It's always in milliliters, some number of milliliters. And H is the potency of the vehicle that we have on hand. That's where the H comes from. That we have on hand in our pharmacy, in our practice, whatever. Well, where do we get that? Well, these two, so D comes from the prescription. If we look on the drug label, okay, let's go over here to our bottle of amoxicillin. I'm going to use the trade name Amoxil because I'm lazy. We're going to see Amoxil, 250 milligram tablets. Okay. That tells us both V and H. Tablets is V and 250 milligrams is H. Okay. So right away, three of those components are known. We know D, V, and H by simply reading the prescription and the label on the bottle. Okay. So again, that is something that is just an ability simply to read, and we can all do that. Okay. So now if we substitute those values into this formula, we get 500 milligrams times tablet. And note that we can have words in our fractions, no problem. Okay, divided by 250 milligrams. So milligrams obviously cancel out because anything that's on both top and bottom of a fraction can be canceled out. And we simply divide 250 into 500, and what we get is 2 tablets. Now, you probably already had that figured out, right? 500 milligram dose, 250 milligram tablets, going to take 2 of them. But again, use this as an example because that's as easy as it is. There's some setup to some of these, for sure. And you do have to think about the problem. I'll throw a little wrinkle into this exact same problem in a minute to show how we deal with liquids. Okay? So, but that's about as complicated as it gets. You know, if you know, obviously, you know, understanding the terms are necessary for actually telling the patient how to take the drug. When you get a prescription, it's written out in English. Take 2 tablets 3 times a day for 10 days. Well, it started off as that. Note, 500 milligrams doesn't enter into that patient description. So it doesn't matter if our drug is dosed in milligrams, grams, micrograms, units, or milliequivalents, because we take the dosage form. Does that make sense? Okay. All of this is pretty straightforward. But as I said, I'm going to throw a little wrinkle into this, and we're going to assume that this is Yoko taking her son to the pediatrician and needing amoxicillin. He's not going to take tablets.
No, they gave him liquid.
They're going to give him a suspension, yeah. Okay, so let's assume that it's the same dose. But we have a pediatric patient. Or perhaps we have an elderly dementia patient who can't swallow tablets. There's another place with that. Or let's assume that the patient is my older daughter who can't even swallow a 200 milligram ibuprofen tablet. She has to have liquids. So there are times when the patient will need liquids. Obviously, PEDS is the most common. But certain very elderly people cannot swallow drugs as well. So we would give them other things. So in this case, again, we have our dose, and what we have is 250 milligrams per 5 ml. Now, it will say here amoxicillin suspension. And liquid drugs can be suspensions or solutions. A solution is clear, sort of like children's ibuprofen. A suspension has solids in it, and you have to shake it up before you dispense it. Okay, not a big deal, but it's something that, again, we need to let patients know how to do this. So in this case, this is H. The 250 milligrams is H, but 5 milliliters is the vehicle. Use the entire thing as written on the label. Don't get smart and say, okay, that's 50 milligrams per milliliter, because it is. But use what's on the label, because the end result is going to be exactly the same. Okay, so now we have an equation that is 500 milliliters times 5, or milligrams, excuse me, I do that all the time, times 5 milliliters divided by 250 milligrams. Again, milligrams cancel out, and we get 500 divided by 250 times 5 is 10 milliliters. That's our dose. Now, unless we have that metric marked dosing, we don't have 10 milliliter dosing oral syringes, but we do have the little cups that can be 10 milliliters. Unless we are confident that the patient can be told to dose in milliliters, we now have to convert that to teaspoons. And remember, from the conversion rubric, if we're going from milliliters to teaspoons, we divide by what? Take a look at the conversion rubric there on the first page, right under household. We take it from quarts down to milliliters. If we want to go from milliliters to teaspoons, we divide by 5. That's why learning this rubric is a good idea. Divide by 5. So here, we're now going to divide by 5 milliliters per teaspoon. And we're going to get 2 teaspoons. And again, when we write this out for the patient, we don't use the abbreviation TSP. We write out teaspoonfuls. because we don't want anybody making mistakes. Does that make sense to everyone? Yeah. So that's how we handle liquid drugs. And it doesn't matter if we are taking these as oral, if it's liquid, all injectable drugs are liquids. So it doesn't matter if we're talking about an injectable drug or an oral drug. We stop when we're doing injectables at the milliliter mark because all of our syringes are graduated in milliliters. Okay. So, and by the way, a milliliter, you're all familiar with the term cubic centimeter or cc. Okay, that's a cube. That is 1 centimeter on a side. A centimeter is about 4/10 of an inch. So it's about yay big. A cube 1 centimeter on a side, by definition, has a volume of 1 milliliter. Okay, and to further unify the metric system, that 1 milliliter, if it's water, weighs 1 gram. So there are equivalencies all over the place in the metric system, which is why it's the preferred system. And that's why our syringes can be graduated in cc's or milliliters, and often both. Okay, because they're the same thing, same volume. We've got about 10 minutes left to class. So, questions? Okay. Pardon?
It's pretty straightforward and simple.
Yeah.
It's not
We'll make it, we'll make it a little more complicated to set up. But I really want you to understand that the math really doesn't get much more complicated than this.
No, it's all pretty like basic
Yeah.
math, and if you had algebra 1,
Shouldn't be, no.
it's really like pretty simple math. It's just like double checking to make sure you didn't do anything else.
Asking yourself questions at every step. Is there anything I've left out? Is there anything else that I need to consider? And then also asking yourself, does it look right? Because you know what else is going on? And here in this class as well, you'll always have calculators.
Yeah, I brought one.
Yeah. Yeah, you can always, I prefer you use a calculator because if you enter the data correctly, calculators are less likely to make mistakes. I do a lot of math in my head, and I can't tell you how many mistakes I make because I'm usually running pretty fast. But I try to keep myself at pace so that I don't make as many mistakes. But it's easy to do. And a lot of times when I'm making up a problem, I'll make it up in my head. I make it real simple for me to solve in my head. But everything is done in a calculator. Use a calculator, always. Then you're going to look at it, and if you did this and you punched in something wrong, say, into this formula, and you came out with 100 milliliter dose, you'd know that was wrong. Again, your instinct is going to say, no, that can't be right. And you're right, it won't be. But again, check it. Calculators are good. They rarely make errors. And usually when they do, it's because of an input error on the part of the user. And calculators are available everywhere. When you take, I used to prepare my students to take the pharmacy technician exam. And they provided a calculator for that exam.
Oh, nice.
The-
A lot of
the,
mathematical things usually don't provide calculators unless it's like necessary.
Yeah.
For admin, like, for junior. But
Yeah.
usually, even when I was in like high school and I was taking all of like my AP like math stuff or like my statistics in college, algebra, trade, and all that other stuff, like they didn't like use a calculator for any of those except like one. They let me use a calculator for like a small section for one of my math courses. That's it. Other than that, I just had to work.
I can't imagine doing statistics without a calculator.
Yeah, well, they let me do it for one section of my AP statistics.
Yeah.
But then they didn't let me use it for the rest of it.
Huh.
Physics, math was the only one I was allowed to use a calculator for everything. Was my AP physics one too.
You should, because some of those calculations can get kind of hairy.
They're really, really complicated.
Yeah, they can be a mess. Yeah, I took before the days of calculators. I was taking physics and various math courses when I was an undergraduate, and we used slide rules, and there was no way not to do that in those classes. But now, of course, everybody has calculators, and somebody says, "What's a slide rule?" But nonetheless, there are lots of ways of doing it. But in reality, these are so simple that you can, until you're really doing weight-based calculations and you've got a patient that weighs something like 37.36 kilograms, you can do everything here on paper as well. But still, use a calculator. Get used to doing that. You'll always have them. And I'm a great believer in avoiding the avoidable mistakes. And paper math has avoidable mistakes. So anyway, so what I would suggest you do is go through this calculation introduction over the next day, a couple of days, or next day or so, and call it up online and look at the videos that are in it. They will help you a lot, give you a lot of good information. Okay. Questions? Now, Katie mentioned that we're doing power hour for an hour after the morning class and an hour before the evening class. If you want to stay and do any of your work, please feel free to do so. I'd be happy to sit in here and be available for questions. If you don't, or you can go in and use the Student Success Center and get one of their snacks. Or I'd be willing to bet that there may still be pancakes and sausage out front as well, since they were having a hard time flogging that stuff off this morning. So, Michaela, do you have any questions? Nope. Okay.